Welcome. This first lecture will introduce you to artificial intelligence and machine learning. We may call it AI or ML respectively. This will be our journey. We will start by looking into what artificial intelligence is, its history, and its relation to machine learning. Then we will center our attention in machine learning, with description of its life cycle. In other 2 mini lectures within this module, we will review some basic concepts and also applications of machine learning applied to biomedical research. So what is artificial intelligence or AI? According to John McCarthy, one of the founders of the AI discipline, AI is, open quotes, the science and engineering of making intelligent machines, especially intelligent computer programs, close quote. The goal of AI has been to create systems that can understand, think, learn, and behave like humans. While artificial intelligence is a broad science of mimicking human abilities, machine learning is a specific subset of AI that trains the machines how to learn. There is a large number of applications of AI in a variety of sectors. In these slides, we are only showing a subset of these as a reference. For example, applications in finance include fraud detection, risk assessment, and forecasting. In education, AI can help with the alignment of course learning objectives and activities, in content preparation, in gamification, and course recommendations, along with creating closed captions and readers and translating content. In transport, we are very familiar with route analysis and price predictions, and we do a lot of personalization. These are all done by AI methods which are used to improve the quality and experience of travelers. The 2 sectors this course is concerned about are highlighted on the right. In healthcare, AI can assist doctors to make better and faster diagnoses, can provide insights and analysis of clinical data, improve patient monitoring, etc. In biomedical research, it can assist in prediction, for example, protein structure, categorization, for example, pathogenic versus non-pathogenic variants, summarization of data, analysis of images, and so on. So these are just a few examples. I always like to start a new topic by providing some historical background, as it helps understanding the evolution of the field and how new developments are many times aligned with the technological advancements. In the interest of time, this timeline shows only a small number of all important events. This timeline starts in 1943, where the first mathematical model of neural network was created. In the 1950s, Arthur Samuel, who worked at IBM, developed a computer program for playing checkers. These programs recorded all the position it has already seen, combining it with the value of a reward function. He was the first to create the phrase machine learning. In 1956, a small group of scientists gathered at Dartmouth summer project on artificial intelligence. And this is considered the birthplace of AI. This was organized by John McCarthy. As you remember, I previously mentioned him when giving the definition of artificial intelligence. The group that worked in the summer camp was called Symbolists. Researchers developing symbolic AI set out to explicitly teach computers about the world. They thought that knowledge could be represented by a set of rules, and computer programs can use logic to manipulate that knowledge. But this school of thought didn't really go very far. Another school of thought, called the connectionist, inspired by biology, work on artificial neural networks that take information and make sense of it by themselves. In 1957, a researcher called Rosenblatt at Cornell, who was a connectionist, combined a model of brain-net interaction with Arthur Samuel's machine learning idea and created the Mark I perceptron machine capable of perceiving, recognizing, and identifying its surroundings without any human control. This machine had 400 sensors. These were light sensors that gathered the information and acted as a retina, feeding the information to 1,000 neurons that did the processing and produced a single output. However, there were many skeptics that insisted that the perceptron was incapable of really reshaping the relationship between human and machine. And then the enthusiasm for artificial intelligence really went down. This was the start of what is called the AI winter in the United States. These were decades of federal funding for artificial intelligence dried up for research. In 1967, there was development of the near neighbor algorithm that was the beginning of the basic pattern recognition. This algorithm was used for mapping routes and was one of the earliest algorithms used in finding the solution to the challenge problem of finding the most efficient route. In 1979, a Japanese computer scientist called Fukushima published his work on the neocognitron, a hierarchical multi-layer network which is used to detect patterns. He used it for handwritten recognition, character recognition, and this inspired the development of the convolutional neural networks that we use nowadays for image recognition. In the 1980s, the boosting algorithm was created, and this was necessary development in machine learning because the boosting is used to reduce bias during supervised learning and include algorithms that transform weak learners into strong ones. In the 1990s, the access to cheap computers turned out to be a boom for connectionists because suddenly they had access to enough computer power to run neural networks with many layers of artificial neurons. And the period of 1995 to 97, key machine learning and deep learning algorithms were born. At that time, also Deep Blue machine IBM beat the chess champion Kasparov. So the World Wide Web blossoms, so finally there's enough data to train neural networks for a wide range of applications. And 2009, ImageNet, which is a dataset containing images labeled to help training deep learning models, was deployed. After that, there were many very rapidly development. For example, Google Brain creates a method for self-teaching to identify cat images. At the same time, IBM Watson machine beat Jeopardy players. In 2014, there's this face recognition algorithm or program called DeepFace by Facebook, Civil Recommendation by Google, and the first chatbot. The last point I will mention is DeepMind AlphaFold for the novel prediction of protein 3D structure, which was awarded the Nobel Prize in Chemistry in 2024. But note that there are many other important events, and the timeline needs to be updated as we speak. One thing that should be added is the development of large language models by OpenAI, which has really revolutionized the field. Now, let's take a look at the timeline through an equity, diversity, and inclusive lens. Take a moment to review the information posted in the link on the left. You will find, not surprisingly, that there were not many contributions by women or people of color described. This has to do with two aspects: some contributions not being recognized and also underrepresentation in the field. For example, in 1940s, the women were tasked to program the first electronic computers, and programming the machine was still closely associated with human computation and was therefore considered to be a type of sub-professional women's work. More recently, attention has been called on the underrepresentation of Black people at two levels: on the data, where that machine models are trained, and the expertise in the field. These are very important aspects, and knowing this gives you a full perspective on AI history, and we will definitely review the impact of these underrepresentations in other modules. Machine learning is a data-driven approach. What do we mean by this? So you have the data that you are in for the task you're interested in. In traditional programming, you will have explicit instructions programmed by humans. So there are some rules and logics that are created, and they are put in a program, and the output is determined by these predefined rules and computations. There is limited adaptability to new data. Whereas in machine learning, the models learn patterns and rules directly from the data. In some cases, examples are given in order for those patterns to be recognized. The focus is on training algorithms rather than hard-coding rules. That is, has to do on being able to generalize and do this pattern recognition. This method, the output of, after it recognizes the pattern, learns the pattern, the output is a learned model. And this is what allows generalization. We can include new data going through this module. It is highly adaptable to new data and scenarios. Thus, machine learning lets data shape the rules, enabling dynamic and adaptive solutions. We know now that machine learning is a subfield of artificial intelligence and focusing on methods for teaching computers how to learn. So how do we know it learned? Quoting Professor Tom Mitchell's, open quote, "A computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at task in T as measured by P improves with experience E," close quote. The task is the exact problem we intend to solve. The experience is learning the inherent patterns from data, and the performance is the measure of how well the model performed the task given the exposure to the experience. And here we're going to review all of this in details. This is the machine learning lifecycle that we can overlap with the learning elements described in the previous slide. Given a question or problem to solve, that is our task, we provide data, we collect the data and train our machine learning, and this is the experience. And after that, in the next part in the cycle, we evaluate how well the system performed based on that experience it was exposed. And we revise the model and then improve and start again. After we have our task to solve, which was the first step in the life cycle, the very first thing we need to do is collect the data for our model to be trained. It is really important to know what data types your data contains to correctly select and apply the methods to the data. Why is this? First, because remember that algorithms only understand numbers. If a dataset contains data that are not numerical, some processing is needed to convert them into some numerical form. On the other hand, I'm borrowing this example from Data 365 website. For example, if you have a data set with a column that contains zip codes and you want to determine its type, the first thing you might think it is an integer because all zip codes have a sequence of numbers. But that's not true. A numerical value can be added, subtracted, and multiplied by other value. So if you do that to zip codes, what you get is really a different number, which is certainly not a valid zip code. And that leads us to understand that zip codes are not numerical values, they are categorical, they are strings. Now that I convince you that data literacy is important, let's review some of the data very quickly. There are two main data types, numerical and categorical. Numerical is the simplest one, data type. It is also the type that is directly usable and understood by most algorithms. Numerical data represents scalar information about entities being observed. Also, the numeric values form the basis of vector features. And numerical values could be discrete. These are particular numbers, for example, counts of something, and continuous, where, like example, a scalar would be a temperature range, or a gradient, like in a vector would be a vector. It would be also continuous numerical. On the other hand, categorical variables are used to represent categories of entities being observed. We have nominal, which define the category of a data point without any ordering possible, in this case chemicals, or could be hair color, which could be black, brown, white, gray, whatever. And ordinal implies some ranking or order. In this case, we have a satisfaction scale. We usually approach quantitative outcomes variables with regression, and qualitative outcome variables with classification. Data can also be described as structure, unstructured, or semi-structured. And here we have some examples. Structured data, like tabular data, conform to a very predefined data model. Semi-structure, like markup language, does not conform to a tabular data model, but nonetheless have some structure. So XML and JSON have this kind of structure. And unstructured data is really not organized or in any predefined manner. So examples are text and media, like images. Now let's play a little game. Take a time to think about where these different variables would be placed if you need to tell what type of data they are. So ethnicity will go to nominal. Molecular mass is numerical continuous. Name of entities like genes, proteins, chemicals are nominal. Number of CPUs, computer power, is a discrete numerical value. A course satisfaction scale could be ordinal. Where placing a competition would be ordinal as well. The order, the rank matters. RNA-seq read count, which would be a number, discrete number, and distance, it's considered numerical continuous. So hopefully you got to the same conclusion as I did. So what is a machine learning model? Basically, a model is the learned representation of patterns from data. It is the output of a machine learning algorithm run on the data. So the reason I'm bringing this up is because I want to distinguish between a model and what is the algorithm. Characteristics of the algorithms involved, they act on the data to create models, and they are general purpose and reusable. So for example, linear regression, decision tree, neural networks, those are all algorithms that we can apply to different data. Whereas the model is dependent on the specific data and task, and we customize to solve particular, as I mentioned, particular problems. In this case would be the trained version of this algorithm based on the given specific data. Going back to our machine learning cycle, the experience part, which has to do with learning, we can describe the methods for learning in terms of the amount of human supervision or involvement in the training. Also, we can describe it in terms of the ability to learn from incremental data. And we also can describe it in terms of the approach to generalization from data. And we're going to review each of these in the next slides. Supervised learning has to do with the amount of human supervision involvement. The model is trained on labeled data, and by labeled data we mean that each input has corresponding known output. That is the supervision part, allowing it to learn the relationship between the inputs and outputs to predict new outputs for unseen data based on patterns identified in the training set. So basically, there is some training data sets where we know the output, and this is given to the systems for the algorithm to learn and then create a model. And then we can process new, after evaluation and we are happy with the model, we can process new data through that model and will give us the output. Supervised learning indicates that you know the outcome of interest. So that's important to know. We know what we want as the outcome. Examples include prediction of secondary protein structure, genome accessibility to genome regulatory factors, healthcare cost in dollars, and so on. Algorithms that are suitable for supervised learning are regression for numerical variables and classification for categorical data. These are just examples. But we often do not have access to pre-labeled training data, and we may still want to extract useful insights of patterns from our data. In this scenario, unsupervised learning methods are extremely powerful. Unsupervised learning is more concerned with trying to extract meaningful insights or information rather than trying to predict some outcome based on previously available supervised training data. We don't know what the output is. We just feed the data, the algorithm extracts some patterns, and then we got some model. And we process our new data on that and we look at the output. Methods include topic modeling, for example, to identify groups of documents that share some commonality, dimensionality reductions like principal component analysis, and clustering methods. We just saw that in supervised learning, training involves examples and their correct answers. We call them labels. The model predicts an answer, and an expert provides the true label as feedback. This feedback is complete in the sense that it shows exactly what the correct action is. In the third type of learning, in this case we call it reinforcement learning, is about learning to achieve a goal, like winning a game. The reinforcement learning agent, in this case, will be the computer, interacts with the environment, which let's say in a game could be the chess positions, makes decisions and is given reward based on that decision or action. In this case, it doesn't receive exact instructions like the correct action. So instead it's given a reward. And in this case, it must learn by comparing past rewards to improve. In this method, the algorithms are rewarded or penalized through trial and error for their decision, thus reinforcing the behavior of the agent in the environment so it can learn to achieve its goal. The ability to train from incremental data is another of the aspects of learning that we talked about, and there are two types: batch or offline and online learning. Building offline models requires training the models with entire training dataset. Improving the model performance would require retraining all over again with entire training dataset with a new one. These models are kind of statics in nature, which means that once they get trained, their performance will not improve until a new model gets retrained. On the other hand, on online learning algorithms or methods, take an initial guess model and then pick up one observations from the training population and recalibrates the weight on each input parameter. One of the big disadvantages of online learning system is that if it's fed with bad data, the system will have bad performance and the user will see the impact instantly. But it's more suitable for real-world applications when there's a need to keep learning and training on new data samples as they arrive. To illustrate the difference between batch and online learning, let's use a biomedical example. Let's consider the scenario where a medical research team is developing a machine learning model to predict the risk developing a certain heart disease. So this is our task, predict the risk of developing a certain heart disease. And this would be based on various patient characteristics, such as age, blood pressure, cholesterol levels, etc. In the batch learning approach, which is depicted on the left, the research team would first collect a large dataset containing patient characteristics and disease outcomes. They would then use this dataset to train the machine learning model and predict the risk of the disease based on the patient characteristics. Once the model is trained, it could be deployed for predicting now the new risk for patients. On the other model, the research team would continuously collect data on new patients and use this data to update the machine model predictions. So this is an ongoing training, and this allows the model to adapt and improve its predictions over time, even if the characteristics of the population change. Let's say that a new risk factor is identified. For example, here is smoking. Now the new important aspect, characteristics, feature, we call it, is identify smoking. The online learning model will be able to incorporate this information and update its prediction accordingly. Thus, the batch learning is suitable for situations where the underlying data is relatively static and does not change significantly over time, while online learning is better suited for situations where the data is continuously evolving and updating the model with new information can improve its performance. Regarding the approach to the generalization from data, we have instance-based learning, which is a type of machine learning where the model makes prediction based on a set of examples that it has been previously encountered on the raw data. So use the raw data points themselves to figure out outcomes for new or previously unseen data samples, instead of building an explicit model on trained data and then testing it out. For example, suppose that a biomedical researcher is trying to predict whether a patient has a certain disease based on their symptoms. In an instance-based learning approach, the model would look at a set of previously seen patients and their corresponding symptoms and diagnosis, and use that information to make predictions on the new patients. So let's say we have a number of records of patients with their symptoms and their disease. And now we have a new patient that has this particular phenotype symptoms. It has fever, doesn't smell, and is coughing. Which one it will look into the ones existing things to see which one fits better. On the other hand, the model-based learning is a type of machine learning where the model makes predictions based on mathematical model and it has learned from the data. It is typically an iterative process where the input data is used to extract features and models are built based on various model parameters. The best model is then used to predict and make decisions. So continuing with our example, suppose that the researcher is trying to predict whether a patient has a certain disease based on the symptoms, as well as some other variables such as sex, age, and medical history. In the model approach, the model would learn a mathematical function that takes in all the variables as inputs and output predictions of whether the patient has the disease. So here are all the different records, patient records associated with diseases and some features from the patient, and then it creates a model. One of the key differences between the two approaches is that in instance-based learning, the model makes prediction based on specific example it has seen before, while in the model-based learning, the model makes predictions based on a more general mathematical model. So instead of comparing a model that was just trained on comparing to existing things, it creates some predictions. Once we have remember in our cycle. We have the data, we have run some algorithm, and we have a model. We want to see how well this model performs, and that's where the performance measure comes in. The metrics we use depends really on the algorithm selected. Here we have examples of performance measures for classification task. And normally you have a confusion matrix for, remember, classifications is a supervised learning method. And where we know what the actual values are, and we have the predictions, and we can compare how well they agree. So this is the end of our first part of the module. Here are some references, and see you in next module to see basic concepts of machine learning.